So let's start. And then today somehow I'm going to go into a little bit more detail, with a little bit more detail into this theorem that we stated. The theorem that states that for simply connected covers, one has with certain extra mild requirements, one has an isomorphism between the fundamental group of the base space and the group of deck transformations of the cover. This I did cover last time. So a deck transformation or automorphism of a covering map is a self-homeomorphism of the big space, the cover, that really sends fibers of P to fibers of P, right? That kind of permutes each fiber. Okay, and they form a group. And now just recall the terminology that a topological space is said to be simply connected if it is path connected. So first of all, and for every two curves between any 2 points, for any 2 curves, let's say between any 2 points, one can always deform one onto the other within the space. So they are always homotopic relative to endpoints. And second, the topological space is called locally path connected if, so locally path connected if, so I have my space, and then locally path connected if every open, if for every open set and every point in that open set, there is an open neighborhood containing the open set, which is path connected. So in other words, like, it doesn't matter how close to the point I look at, there's always an open set therein, which is still path connected, right, and containing my point. Okay, and now the theorem, which says that if X and Y are topological spaces, so here this Hausdorff is really not, the Hausdorff condition is really not required. But in any case, it doesn't hurt me because all the spaces I consider in this course are Hausdorff. But so if I have a covering map and the big space, the cover, is simply connected and locally path connected, then for every point in the big space, so for every point in the cover, for every point in the cover, and every loop in X based at the projection, so for every point here and every loop here, there is a unique deck transformation. So there is a unique self-homeomorphism from Y to Y that permutes each fiber, with the property that the action of this deck transformation on my original point is precisely the action that the closed curve underneath has on the point. That is that the deck transformation sends this point to the endpoint of the lift of gamma, of the lift of the projection, of the lift of this curve that starts in my given point. So So you see somehow what we start with is only a point and a closed curve based at the projection of that point. This curve has a unique lift starting at my given point, right? And I look at the end point, right? And this is what we start with, and somehow the theorem is that this behavior of just sending this point to the end point, to the last point of the lift of the curve that was given to me, is part of that behavior is part of the behavior of a Dex transformation. So this just sending this point sending this point to this point on the same fiber is part of a Dex transformation, and actually that Dex transformation is unique. So somehow the whole behavior of the Dex transformation is just determined by just saying that I want to send this point into this point. So that's I would say it's kind of a really strong theorem, which in other words can be seen as saying the following: we know that this curve acts. We know that this curve acts on the fiber of the base point, so permutes all these points. So we know that that curve acts on this one, so it sends it somewhere. Okay, and that can be extended in a unique way to a self-homeomorphism of all these that permutes each fiber of P. Okay, in other words, I'm to each curve I'm associating certain self-homeomorphism of Y that permutes fibers of P. It permutes each fiber of P. That is an element, a Deck transformation, and that assignment, that to gamma assigns the Deck transformation I just described, is actually a group isomorphism between the fundamental group of the base and the group of Deck transformations of the covering map. Yeah, and then of course later of course one can ask how this about the dependence, how this depends, how this group isomorphism depends on the point of Y chosen, right? And there is an answer, but if I take instead of this point I take another point on the same fiber, the behavior does change. It's not one obtains a different group isomorphism. But this we will talk about later. So for the proof is a bit heavy, but it does have some conceptual components, which I think are nice. So I'm going to fix my point here, of course, my point Y naught, and then the first thing, for any loop in X, for any loop here, based at the projection, so based at the projection of Y naught. So you see any loop. So there you can see the loop gamma, but it's really, I can take really any loop, and then I can lift it, right? And then I can lift it, and I can lift it it has a lift starting at y naught. Right? So that lift, that I don't quite know, I don't want to draw it ending in the same point. But so this lift, I'm going to just denote it lambda of lambda sub y naught gamma. Right? So for any curve here, for any closed loop here, I consider its lifts, and there is a unique lift starting at this one. That lift is going to be the you see the lift of the curve, but I take the lift starting at the point I want to start with. Okay. Now a bit more. Yeah. So actually, yeah. Sorry. Here, actually, this picture here was actually drawn, yeah, to illustrate this. So this. Yeah. Okay. Now, next thing. For each point in y, for each point in the cover, I'm going to denote by delta y naught y any continuous curve from y naught to y. Right. So like here. So for any point, I denote this curve, which goes from y naught to y, by delta y naught y. Right? And then, okay, as a curve, this one, of course, is not well defined, but any two such curves that from y naught to y are homotopic relative to endpoints because of my assumption that y be simply connected. Right? So this one is well defined up to homotopy relative to endpoints. Okay, that will be sufficient for what I want to do. And then what I'm going to then this is kind of this. Then I'm ready to define the homeomorphism I want, at least as a function. And so what I'm going to do is the following. So I look at the picture. So what I have been given in the statement of the theorem is this point y naught and the closed curve gamma. So this is what I have been given, and just with this information, I want to define a self-homeomorphism of y. So just with that information, I want to be able to take any point in y and define for you its image under some function, right? And what I'm going to do is just for any point, take this curve, project it to x, and then take the unique lift of that projection that starts not at y naught, but at this other point, which is actually the point y naught star gamma or star brackets gamma. Okay, take that unique lift, see where it ends, and this endpoint I declare it to be the image of my original point. Okay, so somehow the point is that before starting to define the function from y to itself, what I do is I just fix one lift of this one. Which lift? The one that starts with gamma naught. And once it's fixed, for each y, I take this curve, and then somehow I just in some way, in some sense, I just transport this curve to the endpoint. That's somehow what I'm doing, just transporting it to the other endpoint, and then just see where it ends. And that is how the function is defined. So this is okay, because notice from y naught to y naught, I have any curve in y from y naught to y naught is homotopic relative to endpoints. 2, just the constant curve at y naught, to the stationary curve. Okay, and this stationary curve, you see, like I kind of, it's just, it never moves. But then when I apply the process I just described, it gives me, well, here I have the constant curve based at this point that never moves, and it ends at that point, which is precisely what I want the image of y naught to be under the homeomorphism, right? Because the image I want it to be y naught star gamma. Okay. Yeah, and here I could say maybe that this, yeah, to illustrate that. Okay, so you see, somehow, at least for the definition, for to describe the behavior, one doesn't need much. So it's kind of to describe the behavior of my function, which I want to belong to the group of deck transformations. It's not hard. So somehow what becomes hard is showing that it has all the properties one wants.
Why is it
Um,
couldn't I decide on any other?
No, because you see, I mean, this, like a curve like this, you mean? Let's say, okay, so let's say like this, right? Well, it does project to something, but I mean, actually, you know that it's not going to project to gamma, because you see the theorem from the previous lecture that I can recall in a moment, says that every time if you have one curve in the base space, and you have, yeah. So maybe let me just go back to that one. To this statement. Yeah. So this statement says, if you have your cover and you have a curve in x, so you have your curve in x, then for each point in the fiber of this one, there is exactly one lift starting there, right? So for instance, in this example, let's consider this curve, right? And then in its fiber has 2 points, which are this one and this one. And then as soon as you tell me which point in the fiber you want, let's say this one, there is exactly one lift starting there. So there's exactly one here and exactly one starting here. But so if you go back to this one, I mean, then you apply it to this one, kind of in a way. We know that we took gamma to be a loop, but for a moment we forget about the fact that it's a loop. We just take into account kind of what this point as its starting point, and then for each point there's a unique lift starting there. Okay. Yeah, no problem. Okay. Okay, and now so now, at least now, for each gamma, for each closed curve gamma, I have a function from y to y, right? And now I want several things to happen. I want that function, I want it to be continuous. I actually want it to be a homeomorphism of y, and I also want it to have the property of permuting every fiber, right? So that I want it to have the property that the function that I just constructed associated to gamma, namely namely this phi of gamma, and here why not? I wanted to have this property that this diagram commutes, right? So that whenever I consider any fiber here, phi of that fiber is again a fiber. Right? Sorry, not phi of that fiber is again a fiber. Phi of that fiber is itself. Sorry. Okay, now, yeah, I want that, and I also want the assignment that to each gamma associates the corresponding deck transformation. I want it to be a group isomorphism. Right? So there are several properties to check. Now, consider the situation where gamma, where the function gamma is just the constant function at the projection of y naught. Right? So it's kind of just the constant curve anchored at this point, right? So the curve that never moves. Okay, and then its lift is actually just the constant here. So whenever I take a y here and I take this curve and I transport it to the end, well, it just gives me the same curve. So here this y didn't move. So in other words, the constant closed curve here, the trivial closed curve here, acts as the identity of y because it doesn't move anything, and it doesn't move anything simply because the lift of the constant is just the constant. Okay, so so we have this property. Okay, and now I'm going to now consider two loops based at this point. So two loops based here. Okay, now and we notice the following. Yeah, so consider the lift of gamma starting at y naught. So it's this curve, right? So that curve is this lambda gamma lambda y naught gamma, and then that one concatenated with the lift that starts at this point. That is, it starts here, and it lifts this curve, right? So yes, yeah. So in the end, so this one is this curve, right? So and notice that this curve, the curve it ends up being is just this concatenation, this concatenated with this one, right? So in the end, it simply goes from y naught to this point, and that point was precisely to be defined. It was precisely defined to be the image of y. So in other words, I'm just realizing that this curve, that it's just a curve that connects y naught to phi of y, right? And so it's really, and you see, it's kind of, I can just think of it this way, because any two curves going from y naught to this point are homotopic relative to endpoints, because y is simply connected. Okay, but you see that this means so, you know, or if you want, when I want to take I want to connect y naught to this point, and then I say, okay, I just do it through a convenient curve which up to homotopy relative to endpoints is well defined. Okay, and then what I notice then is that when I consider the projection, right? So when I consider the projection which lives here and here, and you are seeing the projection here. So the projection, this projection, you can see it here, like is this one followed by this one, because here it was this one followed by this one, and you see it starts with gamma, and then it goes with, well, you see this is a lift of this curve. So when you project it, you just get that curve. So this projects to gamma, and this one projects, well, simply to this. Okay, and now I'm going to use that to compute this. So because you see here I took two loops. So far from those loops, I have made considerations only regarding one. But let's see. Phi eta of phi gamma of y. So what's my rule? The rule to define that? Well, okay. So what I can, the rule was, I'm interested in phi eta of this point. So what I'm going to do is I'm going to take a curve from y, sorry, a curve from y naught to y. Sorry. I'm interested in phi eta of this point. So I'm going to take a curve in y from y naught to the point, right? And that curve I'm going to transport it to the end of the lift of eta that starts at y naught. So I take the curve from y to this point. So here you are seeing it, the curve from y to the given point. Right? I project it so that I can lift the projection, and I take the lift that I take the lift that kind of the lift that transports the curve to the end of the lift of eta, so to this point, right? The end of the lift of eta that starts at y naught. Okay, so this is this. So for this, I just did the definition, and this is the lift, and then I just look at where it ends. Okay. Now, this is homotopic relative to endpoints to this one, to this concatenation. So I just substitute. Instead of this, I write this, right? And the point is two things that are homotopic in the base space. The homotopies can be lifted, not only curves. So here the lifts, I can say that are actually homotopic. Okay, and in particular they have the same endpoint, which is what matters here. Yeah, so here that's why I have equality, because the endpoints of the lifts are really the same. So in other words, I'm just using this other theorem about lifting homotopies and not only curves through covering maps. Okay, and so I can make that substitution. And here notice that let's analyze what this does. So for this, I have to so this lift, it starts in y naught star eta, which I have written here. 1 second. Yes. So here, yeah, and then from there, I have to go with uh, with lifting first gamma and then this one. So first gamma, I end up in this point, kind of by definition of this point. That's where I end up, right? And when I'm there, I have to follow with the lift of this delta of y not y. Okay, so I have to do this. So I apply this one and then this one. But how to say? So notice that that's the same. That's the same as right. And then yeah, okay. Sorry, that's the lift. That's the lift. But I have to take the final point. So I have to take this final point. Now, taking that final point, notice that it amounts to just taking the final point of this curve, right? Which it's a lift of this projection of delta y not y that starts at this point. That starts at this point. Right? So in other words, what I'm doing is I'm noticing that to take the endpoint of this lift, so to take the endpoint of this lift, is just the endpoint. It's just the same as taking the endpoint of this, and the endpoint of this is just the endpoint of this lift, right? The lift that starts here. That's all I'm doing. And then here, kind of, I just associate. I know that this is a right action. So so I mean, I know that this point is equal to this point in y. And here I notice that, and here, okay, so here it's concatenation. Sorry, so this one is really concatenation. So I mean, this symbol I should have actually written this symbol. Okay, but anyway, so what I notice is that this is precisely phi of this concatenation of y, right? Because if you ask for how this one is defined, well, you have to take a curve from y naught to y, so that this curve, project it and lift it, and then project it and lift it to this point, to the lift that starts at this point. And then with all these equalities, what I obtain is that this is equal to this, which in the end tells me that since this happens for every y, what I obtain is that this composition is actually equal to this. This composition is equal to this function. So in other words, taking phi of gamma opens the operation of concatenation, and it becomes composition. Okay, so so now I know that this gives me the identity. I know that concatenation goes to composition, Okay, and now I'm going to show that it's continuous. So that this function, that the action, that not that the action of gamma, but that the cell homeomorphism associated to gamma is continuous. Right? So what I'm going to do is, I want to take an open subset of Y, and I want to see that its inverse image under this phi of gamma, is open in Y. So so what I'm going to do is I fix a point and an open set containing the image. Right? Somehow I think of I consider Y as the codom. I consider this copy of Y, the one that serves as codomain. Yeah, and then what I'm doing there is I'm taking this point in the image. I mean, I'm taking this point, and some open set containing it. And I somehow I want to show that the inverse image of this open set is open. Okay, so I'm in this situation here. So I'm taking this point, and I'm taking this open set containing that point. Now, of course, this open set in principle could be very big, right? I mean, and it could be, you see, that somehow that inside that it contains overlapping kind of pancakes. You see, pancakes kind of that lie on the same sets downstairs. But so what I'm going to do is to have better control of that open set. What I'm going to do is shrink it if necessary, so that actually its image is an open subset of X, evenly covered by P. Right. So somehow the idea is, well, I started really with any open subset here containing this point, and that open subset contains some open subset around that point, whose image is evenly covered. Right? And then what I'm going to do is, instead of considering the original open set, I'm just going to consider the shrunk one. And somehow the reason one can do that is one can just, you see, here like here one can just take an open set, even an open set around this point, around the projection of this point, evenly covered. So this one would be evenly covered. Exactly one of those pancakes contains my point. Okay, exactly one. And then that one, which maps homeomorphically to the open set here, that is which is evenly covered. That one I just intersect with my original open subset that I had, and the result is another open subset because I'm just intersecting two open sets. And now the somehow the image of that intersection is contained here, and then it's evenly covered. So that's always possible, like to assume that the open set I started with here has the property that its projection is evenly covered, and that of course it is, this V is actually one of the open sets that are mapped homeomorphically here. Okay, now the point is, so you see, I want to see that the inverse image of this one on their phi of gamma is open, right? So So I'm going to do the following. So around this one, around Y itself, there is a, how to say, so I have this open subset of X, and then I have all these pancakes above it, and yeah, which is the inverse image of this U, which is and so this inverse image is an open set of Y, which you can see there, which is just disconnected. But this open subset contains some smaller open set around Y, which is path connected, and this is because of the second hypothesis that Y is locally path connected. So I have this hypothesis that Y is locally path connected. So this inverse image of U contains an open set around Y, which is path connected. Now, being path connected, this open subset has to be entirely contained in one of the pancakes, because you see here these pancakes within just the union of the pancakes. I cannot go with a curve from one to the other. They are really disjoint. So you see here any curve connecting someone in one of these pancakes to someone in one of those pancakes, any such curve is a fortiori contained in just the pancake where it starts because of connectedness. So this connected open set containing Y is entirely contained in one of the pancakes. But then you see, so let me maybe try to draw it. Yeah, and that one is path connected. But then let's see what happens to the points in this open set under this phi of gamma. Well, what do I have to do? I have to take any curve from Y naught to any of those points. So I can just go first to Y, and then here locally just connect. Right? And this, you have to lift it, kind of to transport it to this endpoint. Okay, so I go and I do this, and here again, since in the end this final curve is a curve connecting someone in the pancake to someone in a pancake to someone in a pancake, is completely contained in a pancake. So it's completely contained in this V, which means its endpoint has to be in V. But the endpoint is the image of this other point that I took. So just so all of this has to be mapped inside this. So this means that this open subset, well, since it's mapped into V by my function, well, it's just contained in the image of it's just contained in the inverse image of V, and that's what I wanted, right? I mean, I have my open subset Y contained in the inverse image of V. And V, you see, and somehow my point Y was arbitrary, and somehow my my open subset was just I just shrunk the original one. So this is enough to show to deduce that my function is continuous. Okay. So what do we have? In particular, you see, when instead of gamma, I take gamma minus, which is gamma but traversed in the opposite direction. That one is also continuous, because here my gamma, it wasn't special, right? It was arbitrary. So this one is also continuous. And I know that you see this function. Now I also know that function is phi gamma inverse y naught preceded by phi gamma y naught. But this I know that this is precisely phi of, and sorry, this is just with a minus, not with a minus one. But this is precisely phi of gamma minus concatenated with gamma. And we know that this, you see, this kind of goes and comes back. I mean, this is homotopic to the constant at p of y naught, which is the identity. Right? I mean, phi of this one is just the identity. This is what we saw here. Or you can even check directly. You see, even without this, you can really check directly that this is the identity. You can just do it. Yeah, let's say that it's a good exercise to do it directly, kind of as a reality check, right? To see kind of if one is really kind of following the argument. Which, on the other hand, I agree that it may be a bit hard to follow at first glance. Okay, but you see, then this one is continuous. This one is the identity. For the very same reasons, this one is also the identity. So for this one, I have found another continuous function, which sends it back to the identity. So it's a self-homomorphism of y. And I would say it's that this property that every fiber of P gets permuted is obvious, right? Because that's precisely what we did. Like any curve, just lift it, right? Lift it. So its endpoint is of course going to go to the same point in X as the endpoint here, because it's lift, so they project to the same thing. Lift it and then kind of just lift it, just transporting it to the endpoint of whatever curve. So it is clear. So it is now clear that it's really a deck transformation. Okay, and now at least I have now a function that to each, well, one has to use these two theorems from the last lecture to see that if now I take any loop in X homotopic relative to endpoints to gamma, one really obtains the same function. And once one has that, then one has a function from this to the group of deck transformations of P. Okay, and well, one has to show that this is a group isomorphism first, but also there's still another assertion here, which is that the element that the deck transformation with this behavior is unique. So in other words, I mean, right now we already have the ingredients to define a group homomorphism and to go and check that it's an isomorphism. But actually, this behavior is realized by only one deck transformation. Okay, so and this I'm going to this part of the argument I'm going to skip. Somehow the strategy is a more or less a standard strategy, which is well, suppose that I have a deck transformation with the desired behavior, and then define two sets: the sets where it agrees with the one that I already found, and the other one where it disagrees with the one I already found. And the idea is that one is going to prove that that both of them are open sets of Y, and since Y is connected, one of them has to be empty. But since in Y naught one has this, right? In Y naught they coincide. This one and this one coincide in Y naught. This one is not empty, so the other one has to be empty. So this one is the whole Y, and so one has this in the whole Y. So that's the idea. And now to prove that they are both open, one follows almost the exact same reasoning that showed continuity. And that part then I'm going to skip, but it's because it's pretty much a repetition of that argument. Kind of the crucial point. The crucial point is that if I have an open set in the base which is evenly covered, and here in Y I have a curve that connects a point in one pancake to a point in a pancake, then that curve has to be entirely contained in the pancake in which it starts. That's kind of the crucial point. Okay, so this about the fact, the proof that both of these are open. I'm going to skip it. And so you see here it's the end of that argument. Okay, so really there's only one depth transformation with the desired behavior of acting in Y naught precisely as gamma acts on the point. It is a group homomorphism because of this equality. So associating to gamma the corresponding deck transformation is really a group homomorphism. And what is actually very easy is to show that it's bijective. So this I just leave as an exercise. Okay, so it's a bit of a heavy proof, but what I want to kind of to stress is that at least the way it's defined is actually very simple to explain, right? It's just you have your point Y naught at which you are kind of anchoring everything, basing everything, and then what you do is, given any other point, how does gamma act on that point, or what's the corresponding deck transformation doing to this point? Well, you just take this curve, the curve that goes from Y naught to that one, and lift it, but lift it so that it starts in this. The lift starts in this point, which is Y naught star gamma, and take the endpoint, and that's it. Right? So, okay. Now of course comes the question of what's the dependence on which point I compute everything at, right? I mean, it was, I think throughout the argument it was clear that I was really using really using Y naught as some sort of a base of operations, right? I mean, it's kind of, I think it was clear that somehow there's some really heavy dependency on which point on the same fiber I take. And then of course there's the question of what's the relation between between one of the isomorphisms to the group of deck transformations and the other, if I consider 2 points in the same fiber, and this is the relation. So you see, one does not have you see, phi gamma of y1 based kind of taking y1 as base of operations is not necessarily equal to phi of gamma taking y0 as base of operations. And the relation is the following. Take how to say, yeah. So take the curve. I have my 2 points. In the same fiber. So this is y0. This is y1. Here is p of y0, which is equal to p of y1. And then take the curve that goes from y0 to y1. Right, so this is this one. Project it. Okay, so my drawing is really terrible, so I'm going to try to do it nicer. Yes, okay, here it comes. This is delta y0 y, right? And then project it, so it looks something like this, maybe. And this call it eta. Right? So this is eta. The point is that since y0 and y really lie on the same fiber, this eta is a closed curve. So on its own right, it has an associated deck transformation, and then an associated deck. It has an associated deck transformation, and then here you have to say, okay, which one do I consider? Because it has an associated deck transformation when I consider the point y0 in the fiber or the point y1. So what I do is I consider the point y0 in the fiber, and then when I consider that one, the relation is this one. So phi gamma with y1 as basis of operations can be entirely described in terms of y0 via this formula, where the information about y1 is hidden in eta. Okay, and so you see these are yeah, okay, so I'm leaving it there, and the proof now is actually not very hard. So you see this curve. You see, if I go first to y from y0 to y1 in y, so I take this one, right, and then I lift gamma, but now starting at y1. So somehow now I start, I don't know, and this is the lift of gamma that starts at y1. This curve, so this curve that you are seeing here, is a lift of, well, when I project, well, first this goes to eta, and this goes to gamma, of course. Right? So it's a lift of this concatenation, and this concatenation, of course, goes to this point, right? But this point is by definition of that point. Well, I mean, its name is y1 star gamma. Sorry, that's the name of this point. So this curve ends up being a curve that goes from y0 to this point and passes through gamma 1, through y1. So passing through y1. So phi, but now taking as basis of operations y1 of this point, what do I have to do? I have to connect y1 to this point. So I have to connect y1 to this point. So let me see. Y1 to, just 1 second, I'm getting I have to connect this one to this one. I'm suddenly a bit lost. Yeah, sorry. Do I have a picture? Let me see if I can do a picture here. Yeah, sorry, because I have y somewhere. I have where do I write it? Here I have y somewhere. Yes, and this y yeah. So to compute this point, I have to connect y0 to y, and then transport. So I connect y0 to y, and then transport using a lift of eta. But a lift of eta is precisely this, because that is how I define eta, by being the projection of this one, and it starts in y0. So I have to transport this one to here. So yeah, and this is then phi eta y0 of y, right? And now this one here, what I have to do is I have to transport this one because it's the curve that goes from y1 to this point, and I have to transport it to using the lift of gamma that starts at y1. So I have to transport it to start here. Okay, right, and this is phi gamma y1 phi eta y0. Oops. Okay, right. And what I see, is that this one, when I project it, it has the same projection as this one, which has the same projection as this one. Because you see, what I did was I started with this one, project and lift here, project and lift here. So they all have the same projection, which means that you see, if I start with this one, in the end, what I'm doing is I'm projecting that one, that I'm projecting that curve, and then I'm lifting it to start in this point, which is, you see, first eta and then gamma. Well, I mean, it's the lift of the concatenation. So this point is this point. Right? If you want, instead of thinking that I take this one, project and lift, I say no. Take this one, project, go all the way, and lift. And then it's okay, go all the way. I'm going through the lift of the concatenation of eta with gamma, because this maps to eta, this maps to gamma. Okay, but so this point is this point. But you see now here I can open, because I know that, I mean, it's a group homomorphism, right? I mean, this we showed before in the previous theorem. So I have this equality, yeah, and this is for every y. So I can say, okay, then as functions, I have you see phi gamma y1, phi eta y0 is equal to phi eta y0, phi gamma y0 as functions, and then say, okay, and then pass this one to the right, but of course using an inverse. And what you obtain is precisely this. Okay, so the main observation is that projecting and lifting is just the same as projecting and lifting in one go. And then it's like, okay, you lift across what? And then you say, okay, across something that precisely lifts the product. Okay. Now, main moral point. They are not. These are the same. In order for them to be the same, you see, if the group is abelian, if this group is whatever group or the fundamental group is abelian, then they are the same. But otherwise, not necessarily. Which I really stress, because I don't know, for some time I actually thought they were always the same. So let me give some example, because I'm running out of time. So let me start with the once puncture torus, because somehow it's in a way the analysis is harder. So okay, so we agreed, right? I mean, so this is a picture that we saw earlier in the course, right? That it's a Fuchsian. This is H modulo gamma. It's topologically a torus with one point removed, and somehow here is more or less sketched how the projection looks like. So you see, this one is a curve that goes like from the point at infinity to point at infinity, and it's the same point at infinity. So somehow it has to look as some sort of loop coming from the unique point at infinity and doing something and going back to that, right? So that's what I depicted here. So something similar with the blue one, right? And then you see here somehow the basic idea is kind of I just took like I just took this picture and sort of deformed it in an ad hoc way. But now for the blue one, it's the same, right? It comes from point at infinity and goes to that same point at infinity, doing something in between. But you see, actually, the only point it shares with the other one is the point at infinity. So it comes, does something, and then just goes back, so that it's only the point at infinity, the one that they have in common. Okay, now kind of the interesting stuff. Let's take this as our first y naught. And then let's take this curve as I wrote it here. So you see it kind of, let's say it goes down and crosses this one, right? So it goes somehow, it like goes down and crosses that one, right? And let's say that it comes back and then I stop. So the lift of that gamma would be like this one, and this is it, right? And so this would be this lambda of y naught gamma, right? And then this point would be y naught star gamma. Okay, and so this is the curve along which I transport things. And then, for instance, let's see what the image of this guy should be on the deck transformation corresponding to this one. So for that, what I have to do is okay. So let me try to do it with that one. So I have to take this curve. Right? So this is my y. I have to take this curve, project it, and then take the lift that starts at the other point here. So I project it and project it, and then somehow I see that I have to cross the blue one once, right? And then it really, since my gamma behaves like this one, somehow the idea is that then the other one behaves like the other one, right? So it goes this, and then here you are seeing the crossing with the blue one, and then here. Right? So here this crossing comes from this crossing. Okay, right, that one, and then lift that one, but so that now it starts here. Okay, but it has to have the same behavior as the original one, so it really has to like start kind of going to the right, and cross a blue one exactly once, and that's it. So somehow the only option I have is go here, cross one, and that's it. Right? So you see, the image of this point has to be this point. Okay, let's do well. If you think about it, kind of the image of this point has to be this point, right? Let's do this one. So for that, what I do is I just go here and then go here, and then I have to project and lift. So project and lift. The first part, I know that it's this one, right? I mean, this I just saw that the effect of project and lift is what I just drew, right? And then here I have to lift something that crosses the orange one, right? And so if you think about it, it's this one here. So the image of this guy is this guy. Now, on the other hand, let's say what was the kind of, you see, the Mobius transformation that sends this one to this one. Which one is it? Well, if you think it's the Mobius transformation that sends this one to this one, because what it does is it maps everything on here, moves it here. It's a hyperbolic transformation. And then you see if you want, right. I mean it. This okay. This I so it moves everything here, right, and it moves it this way, right. It really looks as if it were a translation, right? I mean this way, this way, this way, this way. And with a bit more effort, you can actually see that the image of this point is this point. At least by now it makes sense, right? Because it moves things this way. And yeah, and so the point is that the action of this gamma on the hyperbolic plane is precisely the action of the Mobius transformation that sends this one to this one. That's the deck transformation that corresponds to it. Right. And now let's say now that I take another point. Instead of this y naught, let's take this y. This y1. This one here. Right. And so and then to construct the corresponding deck transformation, I have to. The deck transformation of the same gamma. Well, I recall that I have to lift gamma, but now lift it starting here in this and that y1. So it's this lift, and so this is y1 star gamma. Right. And notice now from and so let's see. Yeah, so take this point, right? So this point, let me draw something. This point, oops. This point goes to this point on the when y naught is basis of operations, and now for y1 now I have to take this other curve. I mean this curve from y1 to that same point, but now the point is it crosses twice. Okay, and then now this one I have to transport it to this point. Okay, when I transport it to that point, you see with some practice you see that it has to go it has to go here. So it actually the image is actually around here. So let me right. And what's my point? Well, I mean, this point is actually kind of far from this point, right? I mean, they are not the same, right? I mean, this point, its image under one of the homeomorphisms is this one, and on its image under the other one is here. So they are really not the same. Right? Which in particular tells me, okay, automatically something I can deduce about that is that the fundamental group of this one for sure is not abelian. Something stronger can be said. Kind of, if one, well, okay, I cannot say it in 1 minute, right? But actually, with this picture, one can prove that it's free in two generators. And now, maybe just to finish, maybe let's do something similar here. So let's take now here, well, this point as a y naught, let's say, right? And I don't know. Let's take a point y here. Yeah, and then let's take this gamma. So let's take this gamma going down. Oops, I'm out of time. But so let's take that one. So which means I take this one going down. Right, so I end up here. Yeah, so let me do it in white. Yeah, so I end up here, which is then y naught star gamma, if this is called gamma. Okay, and then I have to to know the image of this one, I have to project and lift, right? So okay, project and lift. I mean, here I'm kind of not doing all the details because I ran out of time, but that's how it looks like, right? I mean, and I think it's easy to be convinced of that that's the case. I mean, here the projection is a bit harder to draw. Okay. And then something that it's actually that here one can easily see is that actually the effect that this gamma has is precisely translation by translation by 1 unit south. But then if you think about it, when one describes it that way, translation by 1 unit south, sorry, and I should be pointing here, translation by 1 unit south, that description is independent of y naught. I mean, here one exercise, if you want, exercise. Phi gamma y naught at any y is y as any z. Okay, at is y minus I. Thinking of y as complex number and also as y naught as complex number. Okay, but this description is independent of y naught. So this means that if I now take another y1 and I do the same, it's going, and I mean, and I do the same, it's still going to send this one to this one. And this is kind of this still, I mean, in the end, the point is that the fundamental group of this torus is abelian. I mean, it's actually S1 cross S1. No, not S1 cross S1, sorry. It's the fundamental group of S1 cross S1, so it's Z plus Z. Which can be proved with the same theorems, right? I mean, with the same technique, because this one is simply connected, locally path connected. And so you see, I find it really kind of shocking that these two pictures, I mean, somehow they look so similar, but here you can really check that this guy goes to this guy under one of the Dex transformations, and then you move your base of operations a little bit, and then that point and goes then to a completely different point. And then if you want to know, okay, so this point and this point, how are they related? You know, they must be related somehow, and the answer is precisely this formula. So maybe if you allow me to just do that, then I will do it, and then we are done. Right. So here I moved one to the left. Right? So if you think the projection of this one is this delta, but in the other direction. That's this one. Right, and then you see how do I obtain, just 1 second, how do I obtain yeah, this point from this point. So let's see. No, I shouldn't have taken this one. Okay, I should have taken another one that doesn't overlap. But yeah, okay. So how am I going to think about it? Yeah. So okay. Yeah. So let's see. So gamma, this one, as I said, has the effect of the hyperbolic transformation that goes this way and sends each of these to the next one, right? This one to the next one, this one to the next one, etc. So like this to this, and sends this part to this part, etc. Okay, and then somehow I can say something similar about yes, okay, yes, sorry, yeah, and then here I can say something similar. The action here, the action of the deck transformation here sends this one to this one, this one to this one, etc. So so the behavior, it really is it really comes like from yeah, something somewhere. 1 second. So it really comes from somewhere like here. Here, yeah, that's the axis. What you see is kind of so what I want to say is that the behavior here is like this one, dictated by this orange geodesics, and here the action is along this one, dictated by these orange ones. Right, and so now those two Mobius transformations, you see this one and this one. How do I obtain one from the other?